I'm excited to be here. I was originally supposed to be on travel, so at this moment I would have been on an airplane to Washington, D.C. Thankfully, headquarters canceled the meeting tomorrow, and so I am thrilled to be able to be here today, and I'm especially honored and privileged to be able to welcome our guest, Sir Roger Penrose. I'm sure, as you all know, Sir Penrose is a mathematical physicist, and he's renowned for his fundamental contributions to general relativity and cosmology. His work encompasses geometry, black hole singularities, the unification of quantum mechanics and gravity, the structure of space-time, and the very origin of our universe. He is the recipient of the 1988 Wolf Prize in Physics, which he shared with Stephen Hawking for the Penrose-Hawking singularity theorems. He was knighted for his significant contributions to science in 1994. His numerous other awards include the 2000 Order of Merit, the 2004 De Morgan Medal, and the 2005 Royal Society of London's Copley Medal. He is the author of hundreds of articles and several books, including The Emperor's New Mind, which challenged the premise that consciousness is computation and proposes that we need new physics to understand it. And most recently, his book, Fashion, Faith, and Fantasy in the New Physics of the Universe, which is an important critique of some of the most significant developments in physics, including string theory and quantum mechanics. We look forward to hearing his talk today entitled The New Cosmological View of Dark Matter, which strangely and slowly decays. Please join me in welcoming Sir Penrose.
NASA, which I've always respected from, moon travel and all that sort of thing long before. And I've been hearing about the things that they're doing now. Most impressive, the Sophia project. There's another Sophia project which I just talked to last week, which was the robot, and I may say she's not nearly so impressive. Okay, now let's see. I've got two of these things, and I'm afraid all this technology has been devoted to making this ancient technology useful, and so I can give my talk on this thing which I've never grown out of, I'm afraid. So here we have the title, which I hope you can read up there. This is meant to be dark matter down there, I suppose. And we'll see what my view of dark matter is. This should be, I think, that way up. So this is, well, it doesn't matter. Time, you see, we relativists have time going up the picture, so some people like it going that way, but you have to get it used to going up the picture. So this is time, and this is the standard picture of our universe, which expanded from the Big Bang, expansion slowed down somewhat, and now it's accelerated outwards, and we expect that acceleration to continue indefinitely, and this could be the result of Einstein's introduction of the term into his equations, which is called lambda, and that lambda seems to be positive, and that positive lambda gives you this exponential expansion here. It's all in all the cosmology books, at least all the ones I know, and so I was a little surprised how surprised people when this got observed, but I suppose people were getting used to it, they were used to that part of the model. Now you might say there's something missing from this picture, which is inflation. Now, inflation was supposed to have been taking place right very early on in the universe. I'll say a bit more about it in a minute. You might say, why haven't I put it in the picture? Well, there are two reasons. One is, maybe I did put it in the picture, and if I did, it would be tucked into that black spot at the beginning, and you wouldn't know the difference. The other reason is I don't really believe it. And it's one of these things which is very artificial. I can see why people introduced it, and that has some relevance to what I want to say. But for the moment, let's have a look at inflation. And for that, we're going to need a powerful magnifying equipment. And so here we have a magnifying glass. And what do you see? Well, what you see is something like this, according to inflation. In the first, 10 to the minus 32 seconds, a ridiculously tiny fraction of a second, the universe was supposed to have been doing, well, you see, I show that partly to compare with what is supposed to be going on now, this exponential expansion, and there's a lot of it going on according to inflation very early on. Now, it's introduced for some reasons which I consider to be bad reasons, and other reasons which are good reasons. So the good reasons, if you don't have inflation, you've got to have something else which accounts for certain phenomena. I'll come to that in a minute. But the bad reasons, let me give you one of them. People say that the universe is very uniform. It's not completely uniform. I mean, there are people in it and things like that. But it's pretty uniform on the whole. And one of the explanations for that is that there was this initial huge expansion and that smoothed everything out. But that doesn't really work. And just to give you an idea why it doesn't work, I'm turning this upside down because you could consider a collapsing universe. And in a collapsing universe, you might imagine there were a bit of some irregularities going on in here. And these irregularities would gradually magnify and magnify, and they would form black holes, and these black holes would form some incredible mess. And I hope I've got it this right way around. That incredible mess is nothing like what we actually see in the universe. Now, you see, you could put inflation, the inflaton field, or whatever it's called, in order to explain inflation. It's a field which somewhat arbitrarily invented in order to make inflation work. But if you can put the inflaton field, and it doesn't have any effect on this at all, worth mentioning. And so this mess that you get at the end, well, you see the equations of Einstein's theory are completely symmetrical in time. So that means that this would be a possibility for the beginning, inflation or no inflation. Inflation doesn't really get working at all if you have this kind of complicated situation. I should say, and this is important for what I want to say later, the likelihood, if the initial state was chosen randomly, the likelihood of that occurring rather than some kind of mess like this, you can give a probability to that, or the chance of something like what we see as opposed to this, if it was a random choice, would be like 1 part in about 10 to the power 124. And this is a figure you can give some substance to. I won't do that here, but it just indicates how extremely improbable the universe we see is, just from that basis. There may be another reason for it, which is sort of what I want to say. In fact, I'm not going to say inflation wasn't there, because it does do good things, and these good things you have to have an explanation for. But what I'm going to say is that inflation was there, but in a sort of strange way. It wasn't tucked in at the beginning here. It was actually before the Big Bang. Now you could say, how could it be before the Big Bang? Because the Big Bang was the beginning. And if it was the beginning, there was no before, so that's silly. Okay, now in order to make sense of all these things that I'm trying to say, I think maybe I'll use this one more. It's probably a little easier for me to get to, so that's one reason. I hope it works all right for you. I'm going to do 2 tricks. These tricks are things which help you to visualize what's going on. And one of these, it helps you to understand this exponential expansion that we observe, and if it's Einstein's lambda, then it will just keep on going indefinitely. The universe will increase its expansion exponentially, and that's what we're stuck with for the remote future. Now, in order to understand that remote future, you can employ a trick, which is to take infinity and squash it down. Now, that's what I have a picture of here. You can squash infinity down to make it into a sort of finite boundary. Now, I'll give you an illustration of that sort of thing. You'll be probably familiar with this picture and others like it. This is an Escher picture, and it describes a certain geometry which these fish creatures inhabit. And the thing that this picture illustrates is the infinity of this geometry. Now, it's what's called a conformal representation, which means although things are squashed as you get towards the edge here, they're squashed in a very particular way, which is called conformal. That is to say, if you squash, the squashing in this direction is just as much as in any other direction. So the squash is uniform in all directions, and you can see that in the eye of these creatures. The eye is a circle, and it remains a circle no matter how close to the edge you get. So the entire universe that these fish inhabit is represented in this finite picture. It's called a conformal representation of the Lobachevsky hyperbolic plane, and this is called the Poincaré disk, I suppose for the reason that it was actually first described by Beltrami. But that's the sort of thing you find in mathematics sometimes. The wrong name gets attached to something. In this case, it was okay because Poincaré did do it again all over after Beltrami had done it. But they were both great mathematicians, there's no question about that. But anyway, you see, infinity is represented as a finite boundary. And I want to use the same trick to squash down this exponentially expanding remote future into a finite boundary. And the thing is, that trick, well, I'll come to that in a minute. That's one trick. Now, what's the other trick? The other trick is the opposite. I'm going to stretch out the Big Bang to make that into a finite boundary. And so those two tricks are handy to do if you want to talk about either infinity or the Big Bang, and it really helps one's understanding of both situations. Now, I'm going to say something that's a bit different about these two tricks, apart from the fact that one's stretching and one is squashing, is that the stretching works under very general circumstances. There's a theorem due to Helmut Friedrich which tells you if you have a positive lambda, as we seem to see, it is positive, then this is just a general phenomenon, that you could squash it down in this way, provided that, first of all, the material in the universe is mostly without mass, like light, the particles of light, the photons. And the other thing is, well, we have these things around called black holes, which will play a big role in what I want to say later on. But a black hole, this is a space-time drawing of a black hole. Don't want to say much about it, except we have the collapsing material and the light cones there and so on, and the horizon is here. But the thing about Stephen Hawking's great contribution, his main contribution to black hole science, is that they actually have a temperature, and so they radiate. Now you might wonder what that temperature is. Well, the hottest black holes are the smallest ones, and the big ones, the big supermassive ones, are the really, really cold. But the hottest ones, those were the ones which we believe to be there, and that LIGO has demonstrated are out there. Well, the hottest ones will be the smallest ones, and they will be a few times the mass of the sun. And the temperature there would be, well, think about the lowest temperature ever made on the Earth artificially, and you won't be far off. So we are thinking about something which is not really very hot, very, very cold, in fact. So what happens, though, when you wait a long time is that the universe cools down by this expansion, and then that cold black hole will be the hottest thing around, and so the radiation will come out from the black hole rather than going in, and when it goes out, it will take energy away, and taking energy away, the black hole shrinks. And this is what Hawking told us, is that if you wait long enough, the black hole will radiate away and disappear with a pop. I'm calling it a pop rather than a bang. Well, it depends on how you define this thing, but it's very small. The really last thing that really goes off is an explosion of a sort of like a big artillery shell. So it wouldn't be very nice if it went off in this room, but it's not much from the astrophysical point of view. But then there's a pretty big thing just before that. But the thing is that I want to say here is you've got to wait an awful long time, particularly before the supermassive ones go. These things, well, I'll come to them a bit later. The supermassive ones, well, they take sort of a googol years to disappear. What's a googol? That's 1 followed by 100 zeros. So you've got to wait for that many years before these black holes, particularly, say, the big ones, disappear. So you've got to wait an awful long time, but we've got infinite length of time to wait, because this is infinity after all. So, okay, that's fine. And then Helmut Friedrich's theorem will work. And so this is a general situation in the future. It's very different for the past. It's very, very special. And this is, you might say, well, and why am I using this transformation? But it's very special, and this is exactly the thing you want to get rid of. You see, why did the universe start off like this rather than like this? Well, usually people sort of postulate it, and I used to say the Weyl curvature hypothesis or something. It's just a postulate. But what I'm going to tell you today is a model which depends on it being very special. And my colleague Paul Todd in Oxford gave a nice way of characterizing the special situation you have here by saying, yes, this trick works. So I'm going to say the future trick works because it usually works, and it almost always does work. And if you have a positive lambda. The past trick works. You want it to work because that is what we want. So it's a condition that you want the universe to satisfy. And if it satisfies that, you get, well, one of the important things is you get a second law of thermodynamics in the form that we seem to see. Let me say something about this. Well, why do we believe in the Big Bang? Well, one reason, lots of Lemaitre and people solved Einstein's equations, and they find for an expanding universe, you go back and you find this singularity. And then there were these theorems that were mentioned earlier about that Stephen Hawking and I did that show you that this is quite general. You can hardly ever get rid of that singularity. But let me say something else about an observational aspect to this. One of the most important pieces of evidence that the Big Bang really was there is this microwave background radiation, which is coming in from all directions, and it's has a remarkable spectrum. This radiation. You see, this curve that I've drawn here is the Planck curve, and it plots here is it's electromagnetic radiation, so it's microwave like primarily microwave, that's in here. So like your microwave cooker. This is the frequency going in this direction, and the intensity for each frequency going that way. And you find this curve here, which very, very closely, and these are the error bars going here, but they're magnified by 500. So you must imagine these error bars hug that curve to closer than the incline. So these things, the curve is a very good representation of what Max Planck explained at the beginning of the 20th century, and this was the start of quantum mechanics. So if you had his formula that the energy of photons, photons, the word didn't exist before that. I mean, that was that light was emitted or absorbed in units which were some multiple of the frequency. And the energy was a definite multiple of the frequency. And this ratio is called Planck's constant, and this is called a black body curve. What's a black body curve? Well, what it represents is maximum entropy. It's the randomest thing you can have. The entropy being a measure of randomness, roughly speaking, and what you see is in the early universe a maximally random situation. Now, there's something funny about that, and I call it the mammoth in the room, because what is entropy? Well, a measure of disorder. And the second law of thermodynamics, a very important physical law, which seems to be satisfied. I mean, little fluctuations maybe go the other way, but overall, it's a very, very overriding law. And this law tells you that as time progresses, the entropy increases. Well, it remains the same, it doesn't go down. The entropy increases. So, okay, what another way of saying that the entropy increases with time is to say that if you went back in time, in other words, reduced time, the entropy decreases. So you go back in time and back in time and back in time until you get to this region where the microwave background radiation was emitted, very close to the Big Bang. Well, very close. You have to think in terms of whatever it is, 380,000 years after the Big Bang, but that's pretty close on the sort of timescales we're thinking about. And so that, you see, well, the entropy is going down and down and down and down until it reaches a maximum. Well, there's something funny about that. I mean, a maximum, why should it be a maximum when it's been going down all this time? And that's the mammoth in the room. Well, you see, it's not a paradox, for a reason I'm going to mention in a minute, but it's a puzzle. Why should the entropy that you see in this microwave background be so big, yet it must be overall very small? Well, what is it that you're seeing? You're seeing photons coming from interactions with matter, charged matter, And so what you're looking at is light and matter basically in equilibrium. Well, the universe is expanding, so you've got to take that into consideration, but it's still the maximum entropy state that you're looking at with regard to matter and radiation. But what it doesn't tell you is the contribution from gravity. And what it does tell you, though, is that since the entropy must have been low then, because it was going up ever since, it must be very low in gravity. And this is reflected in something else about the cosmic microwave background. That is to say, if you look over the sky, it's almost, the temperature of it is almost exactly uniform. Well, there's a little bit of variation. It's about 1 part in 100,000. Now, there's a little bit more which has to do with the motion of the Earth. So the Earth is, I don't know which way it's going, but whichever way it's going, it goes through this microwave radiation, and it's a little bit hotter in the front, a little bit colder at the back, and that you correct for. But once you're corrected for that, you find this very close precision to uniformity over the whole sky, with little variations, which are important, but little variations over the whole sky. That means that the universe was very uniform. Now you see, that again you might think was an indication of high entropy. Suppose you have a gas in a box. Well, when the thing settles down and becomes its maximum entropy state, it will be uniform over the sky. But if you have something like gravitating bodies, then it goes the other way. They tend to be clumpy things, and the clumpiness increases as the entropy increases, and so the uniform state is a very low entropy state. So what this tells you, this whole story, is that the universe was very uniform and therefore very low entropy and gravity, and this is what the universe made use of. As time went on, you get the, well, I was just watching a nice demonstration of how clumpiness can arise, just in another room here, how clumpiness can arise with the initial material, or dark matter it was, we'll come to later, which has a little bit of an irregularity originally, and then it increases as time goes on, and then it forms stars, galaxies, and things that we know that are interesting out there. And this represents an increase in the entropy in gravity, and there is this huge potential for an increase, that the low entropy in the gravity is something which is being made use of in the universe by this clumping, and the fact that you then get stars and things that we like to have out there and very useful and important for us and so on in different ways. Anyway, the point is that all this story is that the universe was indeed very uniform. Well, you see, I used to have a way of saying this in terms of what I call the Weyl curvature hypothesis, and to explain what that meant, I'd have to say what the Weyl curvature is and so on and so on. But my colleague Paul Todd had a much nicer way of saying it, which is also much nicer mathematically, which is to say, you can stretch out this Big Bang to something nice and smooth. So the picture I've drawn you here works, well, in the future, just because it pretty well always works, with a cosmological constant, which is positive, and in the past, because, well, it seems to be true of our universe. But then why was it true of our universe? Now, the thing I want to say here is this, up to this point, I've been saying things which are not particularly revolutionary or unusual. It's just a way of looking at things in a sort of geometrical way, which I like, but people aren't going to complain about it. But what I'm going to say next is something which people do complain about. And I got lots of complaints from different directions. But nevertheless, let's have a look at it. What I'm saying is, this is more like the universe than what I just showed you. By that I mean, you see, this is us. This is, I'm now going to call it not our universe, but our eon. Our eon started with the Big Bang, and it did this expanding and then this exponential expansion. There was an eon before ours, I claim, and there will be another one after ours, and these things presumably go on indefinitely in both directions. Now, the thing is, you can stretch out the Big Bang, squash down infinity, and you could do the same to the previous eon. I'm going to say they're more or less similar, not exactly the same as each other, but more or less the same overall, and that it's the previous eon's remote future, when squashed down conformally, and when our Big Bang is stretched out conformally, you can match them so that they fit exactly. So this is the claim, or this is the model, if you like. And Well, it's a nice piece of geometry. You might say it's a nice way of looking at a picture. It's a nice picture. Why not? But I'm going to say something that it also makes sense physically. Now, this is important. Now, one thing, you see, you might say, well, the remote future is going to be pretty cold, as I was just saying, and the Big Bang is pretty hot. But then that's completely different, isn't it? Well, you see, when you stretch the space out, you have this notion of momentum and energy, and they go in the opposite direction from space and time. So when the space gets stretched, the momentum goes down. When the time gets stretched, the energy goes down. And this is the way things work in physics. They're sort of opposite things. So this means that when you stretch the Big Bang out, the effective temperature will go down. And when you squash infinity down, the effective temperature will go up. And the idea is that they actually match as you cross over. Now this, of course, all depends on, well, yeah, I'm going to say that the physics makes sense as you go across. Well, why does it make sense? This is an important thing. Well, how do we measure geometry in relativity? And people used to give pictures in the old days with little rulers and things like that. And I suppose the idea is you think of ideal ruler as being the meter rule in Paris or something, but that's no good for current measurements. Rulers are pretty useless. What are good are clocks. Now, clocks are extraordinarily precise. I mean, for example, one of the most Einstein introduced the idea of time dilation in the gravitational field. You see, when you have a clock down here, it runs more slowly than the clock up here, and the original observation of this with a huge tower. But now you can measure the difference. I don't know exactly what the difference is, but from here to here. And the clocks are so precise that you can tell the difference by the accuracy in clocks that we have, which is extraordinary. Now, there's a good reason why clocks are so accurate, and this has to do with, let me just show part of this, I think, here. It has to do with the two most important equations of 20th century physics. I don't know if that can be seen very well. Can you see it now? Or is it backwards? I have this little problem with my eyesight, which means I can't see things very well. So, when they're small. I hope that's the right way around now. Okay. Now, the thing is, the two most famous and most important equations, simple equations, of 20th century physics, well, one of them has to be Einstein's E equals mc squared, and the other is Max Planck's E equals h nu. Nu is the frequency. Some people call it F or something, but I learned it as nu. Never mind about that. But the first one, Einstein's one, tells you that energy and mass are equivalent, and Planck tells you, which of course came before Einstein, I should say. This was Max Planck's thing that I was telling you previously. That tells you that energy and frequency are equivalent. If you put the two things together, that tells you mass and frequency equivalent. So if you have a stable particle of a definite mass, then that is a pretty perfect clock, just from these two formulae. And these are the formulae, and you put them together. So that tells you a clock, a particle, a stable particle of a definite mass is an almost perfect clock. And it ticks away according to this frequency. It's not what you actually use directly, because that frequency is enormously high, so you have to scale it down, and you don't use just one particle, but the clocks really do depend ultimately on this fact, which is so fundamental, because it's those two fundamental equations, that mass and frequency are equivalent, and so therefore a massive particle is a clock. And these clocks are so precise that, as I say, these things I was just saying, and the meter rule, well, you don't do it that way. You do by the light travel time it would take to go a meter, and then the meter is defined. Well, let's not go into all that. But then there's an opposite to this, which is in the picture I'm saying here. You see, this cone I've drawn is the light cone, which you have to imagine your space-time has light cones drawn all over it, and that represents what light would do if a flash of light occurred here. How would it spread out into the future? And that's what that cone is. And you sometimes draw the past cone too, as light coming into that point. But it's not actual light, it's just potentially there. So the universe has the cones which tell you more or less how the space and time scale with respect to each other. And that is something to do with light or massless things. But if you have a mass, then you need more, you see. And what these surfaces are here. And let's just to say that in terms of the metric of space-time, there's this quantity, what GAB, G mu nu, whatever it is, which defines the scaling, if you like, the metric of space-time, and it has 10 components. Now, 9 of them, or really the ratios of those 10, define this cone. And that things without mass have to respect this cone. Photons have to respect the cone. But the one extra parameter, that is the scale, if you like, or the 10th parameter, is telling you these surfaces which I've put in this picture here. And they tell you how clocks, identical clocks, zipping at different speeds through this point here, the first tick, the second tick, and the third tick, the clocks measure the crowding of these surfaces here. So the full metric is not just the cones, but how crowded these surfaces are. Now you see, that's fine. That tells you what you want for general relativity. But if you have massless particles, and here we have one, a photon, zipping along like this, it never hits the first of these cones. It doesn't experience the passage of time at all. And so if you only had particles with no mass, you wouldn't need the cones. You wouldn't need you just have the cones. That's all you'd need. And that is the conformal structure, and that is what you match from one eon to the next. So you match the cones, but you don't match the scaling. In fact, I've got pictures doing that, so it gives you some idea. You see here is the future picture, and I've got it all written down here. For all I know, I've got it backwards. Yes, I have. I've got the figure of 10 to the 10 to the 124 and things like that, and the Weyl curvature hypothesis. Don't bother to read all that. All I'm saying is that this is the Big Bang stretched out, and you see the cones are sitting there perfectly happily. There is perhaps something else. Yes, I should say something about this. You see, physically, this Big Bang can be thought of this way because, well, you've got particles as you go further back into the Big Bang, go back in time, the temperature goes up and becomes extremely hot. It becomes so hot that particles which are whizzing around at a huge speed, and the massive particles, they have an energy from their mass, but when that energy goes up and up, their mass becomes completely irrelevant, and so all particles become, in effect, particles without mass. But since they're particles without mass, this picture makes a lot of sense. Let's look at the other one first. I think that's the way around I should have done it. What about the future? Well, this is the picture I had before, which I said in general will hold. If you have nothing which has any mass, and I got rid of the black holes, and they pretty well go into photons, and all the hugely dominant particles around will be photons. However, there will be a few other particles around, so you have to be a little careful about this. Not just photons. In fact, you'll have electrons and positrons. That's the antiparticle of the electron. You might have protons around, but maybe they decay and they end up with positrons. You can't get lower than the electrons and the positron. There's nothing lighter than them which has charge. And you can't get rid of the charge because, well, the ones get sort of isolated from each other and they'll be sitting there. So it's not quite true what I said about nothing left which has no mass. So, and here is something which is a postulate. Some people call it the weakest part of the theory. I think they might be right, but in this theory you do need something like this, that the mass of things like electrons finally has to fade out. It's not that they annihilate with the positrons, because they won't find them. You see, up here they can't find each other. So they've got to be sitting there. But the idea then is that there is some reason that the mass fades out in the very, very remote future. There's no evidence against it. There is a certain amount of evidence, theoretical, that says there's nothing against that happening. And just mention this to the experts here, perhaps. See, there's a thing, when you do particle physics, one of the crudest classification is what the particle's mass is and what its spin is. And what you do is you classify particles according to what's called Casimir operators for the Poincaré group. The Poincaré group is the group of special relativity, and the Casimir operators are things which commute with everything, and so they're completely conserved. So this tells you the mass ought to be completely conserved. And that would contradict what I'm saying here. But The Poincare group, that's the group of special relativity, doesn't have the lambda in it. So when you put the lambda in it, you have something called the de Sitter group. And the de Sitter group, these things aren't Casimir operators for that. So you will start to feel out the cosmological constant, and this tells you that the mass maybe isn't going to be constant because it doesn't have to be constant by the general principles of particle physics. So, okay, it's not a proof it doesn't, that they fade out, but it's consistent with that. So what I'm saying is that according to this scheme I'm describing, the mass will ultimately fade out after a huge length of time. Okay, that's nice for the picture because it says, okay, physically, this future infinity is a nice physical thing. Everything will be massless up there, or asymptotically massless. And so they say, where are we going from now? Which perfectly I could go up here. They keep thinking, well, they don't think anything, but, you know, physically. And so this boundary looks as though it should be continued. And the other way, because the particles get so hot down here that the mass becomes irrelevant again. And so the picture is there should be something on the other side here from where did they come from and where do they go? Well, this picture provides an answer to that question. Where they came from was the previous eon, and where they go is to the next eon. And the cones fit together, and that's the idea. Of course, we don't know it's going to work. You need some mathematics to make it work. You need some observations to make yourself believe it, and things like that. But this is the scheme, and it makes a thing which does fit. That's really what I'm saying here. Physically, as well as mathematically, it does fit. Okay. Now, there are a couple of questions I want to say. I did talk about the second law of thermodynamics, which says entropy goes up. And if you think about this, you might say, well, how can entropy be going up and up and up and up and up and up and up when this picture is supposed to be, this one universe is more or less like this, and so on. So there's a little puzzle there. Well, I must say I was puzzled by that when I first thought it, because the picture is driven by the second law of thermodynamics. That's the whole point of it. And then you say, well, how does it make sense in a cyclic type model? Well, here is where I'm going to be a little bit controversial in another way. I don't know which way around is the best way to do it. Let's do it this way. Where is the most entropy in the universe now? It's in black holes, and it's absolutely hugely in black holes. That is to say, there's so enormously more entropy in the black holes that we know now than in anything else, particularly in the huge supermassive ones that we find around in places. I'll say a little bit more about that later. What happens to them? Well, remember my picture here of the black holes going off pop. You might ask what happens to the entropy or the degrees of freedom in the black hole. Now you see here, and I can't read all this, but I think I'll just tell you the main point, is that Stephen Hawking, who introduced this idea after all of the radiation from a black hole, Stephen Hawking, at one point, he changed his mind. At one point, he said, information or degrees of freedom get lost in a black hole. Information gets lost. And this caused a lot of people to worry. And then, later on, he changed his mind and said information doesn't get lost. It somehow comes out in the radiation. And so whichever view you like to hold on this, you've got Stephen Hawking on your side. Which is kind of handy. But although he wasn't on his own side, so that's slightly worrying. I think he was right to start with. And I'll have a bit more water, I think that might help. I think he was right to begin with, and that the information does get swallowed by the black hole. If you look at the conformal diagrams and things, it's pretty hard to see how anything else happens. But the trouble is, it contradicts a basic thing of quantum mechanics. There's a thing called unitarity. Another way of saying that, you're pushing, are you saying, sure? You're not, okay. A thing called unitarity, which is basically the Schrödinger equation, which tells you how the quantum state evolves with time. And unitarity is central to quantum mechanics. And so if you have information loss, that's going to violate unitarity, and the violation of unitarity is a violation of quantum mechanics as we understand it. And I think that's why Stephen and other people came around to not losing information in the black holes. But to me, I've always had this feeling about quantum mechanics. You see, it contradicts itself, because unitarity is this underlying principle. But whenever you make a measurement, you violate it. And it's sort of kept quiet. People don't say, no, it's violate. Well, yes, there's a little bit of a problem there. And, well, people usually eventually say, oh, well, it goes into the environment or something. These things don't work. The only thing you're really driven to, if you follow the logic of it, is this system which is called the many worlds interpretation of quantum mechanics, which says, well, Schrodinger's cat, which is dead and alive at the same time. There's a universe sort of it splits in two, and there's a dead cat in one and the alive cat in the other. I don't think that really works either, but it's really popular with the philosophers in Oxford, particularly. See, I think that you just take what you see, and what you see is that either the cat is dead or alive, and already the cat thinks so. It's alive. Well, if it's alive, it thinks so. And if you look at the cat, you can see one or the other. And that's what's happened. The world does one or the other, and it doesn't preserve these superpositions at the level of a cat. I'll say a little bit more about that later, but that's a belief that I hold, and it seems to me that tells you already that unitarity is violated every time you make a measurement. And I have reason also to think that violation is to do with bringing quantum mechanics together with general relativity. So there's a tension between those two great subjects, and this tension is something which, to me, is saying, well, I'm not saying one wins over the other, but I'm saying that you've got to recognize that general relativity has an effect on quantum mechanics, and this effect could be what gives you the one or the other that you need for Schrodinger's cat to not be dead and alive at the same time. And it's needed for measurement in quantum mechanics. Okay, that's a little bit of a long story. For the experts, this is a picture of phase space, and it explains how I think things involve. Usually in your phase space, you represent the state by a curve, and then when your black hole disappears, or whenever you like, you lose that information, and you lose some phase space. You squash your phase space down to a smaller space as the thing evolves, and that makes it consistent. But you've got to have something which extends you from current physics to something beyond that. And that extension, to me, is absolutely essential for all sorts of reasons. And this is what you need. You see, let me say it a little bit more in the terms of the picture of the evolution of the universe as I have it. This is conformal cyclic cosmology, I call this model. The evolution of the universe. Well, you see, as you go along here, the entropy is increasing, goes into black holes. The black holes disappear, pop, 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 after a while. And as they go, they swallow information, they swallow degrees of freedom. And this means that when you calculate the entropy, you have to say, oops, I don't take those into account anymore. And that means your entropy effectively comes down. It doesn't come down, it never violates the second law. But the useful entropy that doesn't have to take into account those useless degrees of freedom which get swallowed by the black hole, that effective entropy does come down, and that makes sense in this picture. I don't think I want to say more about this, but I just say that, yes, it does seem to make sense. But you do need this view of information getting lost in black holes. That's crucial. Okay, well, that's the theory. Is it true, this model? Well, of course, that you'd like to know. I'd like to know. Is it true? Well, I did wonder about observing things, and the main thing I thought of, you see, I wondered, is there anything that could get through from one eon to the next? I used to give lectures on this and thinking, well, nobody's ever going to know, so I can talk about this happily, and it will never be contradicted. But then I did think of something, well, maybe something could get through, and I tried to think of what's the most violent thing I can think of. Apart from the Big Bang, the second most violent thing I can think of. Well, we have at the center of our galaxy a supermassive black hole which is about 4 million times the mass of the sun. That's where all the entropy is in our galaxy, pretty well. We are on a collision course with the Andromeda galaxy. The Andromeda galaxy has a black hole quite a bit bigger, 10 times as much. I'm not sure exactly the figure, but quite a bit bigger than ours. We are on this collision course, so we're going to collide. Well, it might be fun to watch it happening, but it'll be rather slow. You have to wait a long time. You have to wait a few billion years before this will happen, so you're all right. But the collision, most of the stars will miss perhaps all the stars will miss each other. The galaxies might swish around like this. They might go through each other. If they do, they'll come back, and the black holes probably won't hit each other the first time, but eventually they'll feel each other out, and they'll spiral into each other, and bang. Well, actually, I'm not sure it's louder than that, because the bang will be in gravitational waves, and you can't hear them. So I don't know if I could call it a bang, really. But it's a huge explosion. An enormous amount of energy will be released. And this energy will work its way up. This is the picture I've drawn here. This is the previous eon, and now I've got these black holes running into each other, bang, and then another one happens, bang, after it swallows another. In a cluster of galaxies, you probably have one dominant one which swallows the others, and then you'll end up with just one super-duper one there. And then Hawking's radiation has to take over, and you've got to wait for these googol number of years, and so on. But in the explosions, you see these effects will come out and hit the squashed down infinity and come through on the stretched out Big Bang. And you could, in principle, looking back, this is us up here, looking back, this is our past light cone, at these explosions. And you should see them as rings in the sky, which you could either characterize as being slightly warmer than the average, that's when the signal is coming in our direction, or slightly cooler, that's when the signal is going away from us. Strangely enough, it's the distant ones which will be warmer and the close ones which will be cooler. So it's the other way around from cosmology. You have a blue shift from the distant ones and the red shift from the close ones, which is a little bit strange to get used to, but that's the way it is in the theory. And these things, you would see that in the rings, or you might look for several rings and look for their concentricity. I have rather than telling you about all this, which is going to take up too much of my time, I've just got references. Really what I want to do is to draw your attention to the last one here. Some of the earlier ones I did with a colleague, Vahe Gurzajan, and most of the three others here down are to do with observations or analysis of first the WMAP data and then the Planck data. These are two satellites which looked at the temperature variations in the microwave background. And the latest one has been just recently published in the monthly notices of the Royal Astronomical Society after many, many tassels with referees. And they said, look, we're not sure, we'll do this. And they say, well, okay, we'll do that. I don't quite see why. And then another one, they said, look, no, you've got to do this. They kept bouncing back from referees. And finally, the referees gave up. They couldn't think of anything else to tell them to do. And so they said, okay, we'll accept your paper, but you must say in the beginning, it might be a chance effect. They say that the signals are there, but it may be just a fluke. And in the paper, it does explicitly say, from their very detailed analysis, how big a fluke it has to be. Well, what they say is the chances are 124 to 125 that it's a real effect, and 1 out of that it's a chance effect. So this seems to me a good indication that it really is a phenomenon that's there, and you've got to take this model seriously. It doesn't say that it's only this model. It just says that you've got to consider this model seriously. And I think that's correct. Okay, now I haven't got onto the subject of the title. I'll leave that there for the moment in case anybody wants to take note of that reference. I mean, the other references are important too, but I'll say that one particularly. I can't probably get them all there at the same time. Okay, now dark matter's in the title. Where does that come in? Well, there's a curious thing about the curvature. Let me just mention this here. I can't go into the details, but it's something I noticed about the Weyl curvature. The Weyl curvature is the conformal curvature. This tells you the curvature which doesn't have anything to do with the scaling, just the light cone structure, if you like. The conformal curvature, that's the Weyl curvature, and it is therefore a conformal thing. And therefore it has a way of scaling. You see the big omega there I've got is the scaling factor. So you can change your metric, that's the G, by multiplying by the big omega. And the thing is, what does the C do? Well, if the indices are all at the bottom, it goes as you see here. But there's another thing, which I'm calling K, which is just the same as C, if you're not interested in these rescalings. But when you rescale them, k scales differently. What do you want k for? Well, k tells you how gravitational waves propagate. And it tells you that if you change the scale, the k still tells you how the gravitational waves propagate. And so if you want to get all the way out to infinity, it's k that the waves respond to. And that means that at infinity, the k is still there, and it tells you the strength of those gravitational waves. It doesn't fade away to 0. That's the scaling's taken care of here. The k tells you how strong the waves are. But it's related to the c in such a way that the c has gone to 0. And so that means that your Weyl curvature has to be 0, and that means on the other side, it's 0. And then the k scales the other way, and this tells you that the gravitational degrees of freedom have gone. And this gives you the picture that I've just shown you, that this very uniform universe is a consequence of this picture. But you have to worry about where have those gravitational degrees of freedom gone. And this is where you have to do some serious mathematics. And I'll just tell you, I won't do the mathematics here. Here is the previous eon, this is the next eon, and these are the g's, and this is where they scale. I have the big omega at the bottom, which is big. I mean, that's a big scale factor, and that represents the squashing down of infinity. And then its inverse, or minus its inverse, is the little omega, and that tells you how much you've got to stretch in order to get the Big Bang. And they're reciprocals of each other. That's the reciprocal hypothesis I introduced. And this all works very nicely. I won't go into the details of this, except to tell you that how the equations work is it tells you that you introduce this conformal factor, and you can write down Einstein's equation in such a way that it's completely invariant under the conformal rescaling, and that allows you to continue out to infinity. So you can do it out to infinity. That's fine. It's just the omega just is a helpful thing. You introduce it to tell you how the equations work and make them consistent. But when you're on the other side, the omega behaves like a physical field. This is the big omega, behaves like a physical field over there. And I won't go into the details, but it's got an energy momentum tensor, and it fits together all nicely. And what is that physical field? Well, you see, in order for the equations to work, you've got to have a dominant new material which wasn't there before. And it has to be a scalar field. So it could be particles without any spin. Well, it stares you in the face, it seems to me. It has to be dark matter. Dark matter, we don't know what it is anyway, so it's allowed to be this. So that's fine. Nobody can contradict me so far. And that's the capital omega. And this, I don't think probably you should read what it says here, but I can't read it myself. So the point is that the big omega behaves like a physical field. Now, it has the property, since it picks up the gravitational degrees of freedom. The gravitational degrees of freedom are sitting there, and they want to know where to go, and where they go is into a fourth derivative of this scalar field. So the scalar field is a little bit irregular because of the gravitational radiation which went in before. And all the degrees of freedom, well, half of them are captured by this field. The other half are captured by a kind of curvature in the initial surface. I don't know what to do with that, but let's not worry about that. I'm talking about the half, which does get through and is the fourth derivative of the omega. Now, this scalar field, I'm saying it's dark matter. Well, it has a lot of properties of dark matter. As far as we know, dark matter only interacts gravitationally. Well, these things only interact gravitationally. They are sort of gravity in a kind of strange form as they get across. I'm calling them eribons. Why do I call them eribons? Well, I thought I needed a nice god to describe, to name these things after. And I looked up in Wikipedia and I saw there was no Greek god, but there's an Egyptian god called Erebos. And then I gave a talk and I said there's no Greek god. I'm going to improve that because I looked up Wikipedia again and it had changed its mind. And now it is a Greek god. They didn't get rid of the god, which was, thank goodness. But the god is a Greek god, and so it's respectable. I don't know why Egyptian gods aren't respectable, never mind. Anyway, it's a respectable god, and he's not just the god of darkness, he is also a primordial god, which is just what you want. So these things are eribons. And the eribons Well, you see, how do they decay? They have to decay because they were there at the beginning, and so they shouldn't build up. You've got to get rid of them before the next crossover, and then you start all over again. So how do they decay? Well, the decay, since they're only gravitation, they have to decay into gravitons, or into gravitational waves. And what's the mass of these things? Well, since they're only gravity, they have to be a Planck mass. What's a Planck mass? Well, it's something like, I'm told it's the mass of the eye of a flea. That's not very much in ordinary parlance, but it's huge for particle physics. It's absolutely enormous. And then I asked all my cosmology friends, is this all right? Can dark matter be the mass of Planck mass? And they say, yeah, sure, there's a huge range of possibilities. Planck mass, well, it's good, fine, if you can do it. So anyway, that's what I'm doing. Now, it goes into gravitational waves, which you say maybe they could be detected by LIGO and all that. Well, that would be exciting. Maybe they can. Maybe they have been already, which would be interesting. Now, I wondered about what sort of form they would be, you see. Well, all this Planck stuff comes in. So how do they decay? Well, they decay into presumably Planck frequency. Well, that's huge. That's 10 to the 40 hertz or something. It was ridiculous. So you wouldn't see the frequency. But what you would see, and this I haven't really time to go into this, but you could see what the effect of high frequency gravitational wave would be. It looks like a matter wave. It's as though you've got a gravitational wave squashes one way and stretches the other way, and then the next time it squashes this way and stretches that way. It oscillates between the two, that sort of thing. But here you have something where you don't see that oscillation. You only see a residual effect, which is an overall squashing in all directions. And that's what this pictures is supposed to be telling you. And so you can understand that from just straightforward geometry. I'm sorry? Oh, it's the wrong way around. Is it? I'm liable to do that. You should have a word which I admit. Oh, yes, of course, the wrong way around. Yes. Okay. Now, these eribons and their decay do two things. I really initially thought about this in discussions with Christoph Meissner, I should say, who's the main person in the Polish group whose reference I put up there. He's been important in the development of these ideas, and we were trying to think of what could cause the microwave background to have its exponential, I should say self-similar these temperature fluctuations have a kind of self-similar character, which is one of the good reasons for inflation. I said it had good and bad reasons, and that one is really needed, but I'm having inflation before the Big Bang, and so you've got to have something which the eribon decays would be the candidate that I suggest for these fluctuations. So I have two places where the eribons become important. I think this is one slide, and it's probably backwards again. I want to show you one last picture, which I think I put up here, which shows you where both of these decays come in. One of them is in the previous eon. These decays would give you this, because of the exponential expansion here, they would, on the other side, give you fluctuations in the temperature which agree with what inflation predicts. That is to say, you have this remarkable scale invariance, not quite scale invariance, but almost scale invariance in these temperature variations. And so that would be a way of doing that. That needs more thinking as well, though. But the other place is we might see eribon decays in our eon. And this is interesting because they could affect gravitational wave detectors. They wouldn't be what the gravitational wave people would expect, because they expect squashing this way and stretching that way at the same time. And it's all set up to look for that. But these squash in both directions, so most of them they wouldn't see. But if they come in along one of the arms in the LIGO machine, go this way or that way, or somewhere close to that, then they would affect not this one, but they would affect the other one, and so you would see them in their signals. So although it would be probably down rather, you would in principle see these things. If they're close enough to us, they would look like blips. Am I red? Am I red yet?
Yes, you're.
They would look like little blips, and maybe they are seen. Maybe you would see them if they're close enough to us, say within the moon's radius from the Earth. I haven't quite worked out how many you would see in a year, but probably quite a few, and there's no reason why, if your detector was sensitive enough, I'm not sure that it is, but you might actually see them as just blips in the data. The other possibility is you might see them from distant galaxies. Then you would have to see some feature that the decay from those distant galaxies would have, and there would be some shape that you could identify as coming in these signals, and you might get a fix on them from where they are. That's something I could say more about, but since my time is up, I think I'll say stop at that point, but just point out that these error-bonds could possibly be seen if they're there, and I think there's a good chance they are there, because the theory seems to be confirmed on the rings. If they are there, you might see them in the cosmic microwave background, have a better explanation for that, or you might see them in our eon. And so that's what this picture is trying to say. And thank you very much.
Thank you very much. And I think we have time for a few questions. So if you'd like to ask a question, please raise your hand and wait for a microphone to come to you. And please do limit it to one question. Go ahead.
Hi. I'd like to. Light's not on. Light is on.
Go ahead.
I'd like to better understand the future conformal. I'd like to better understand the future conformal squished transformation you have and its physical implications. So it's at a finite conformal coordinate in the future, but isn't it still at infinite proper time? And so wouldn't any energy from a black hole collision before then be infinitely attenuated?
You just have to look at the way things scale. You see, this is actually in the K thing, but I sort of raced through that rather. You see, there is the intensity of the radiation, well, it falls off as you get away from the source, but if it hits the surface, the way the conformal factors work, it just falls off as a wave would. I mean, if it was, say, think of electromagnetism, that's easier, because then electromagnetism is completely conformal invariant. Maxwell's equations are conformally invariant. You can squash and stretch different rates all over anywhere you like, and the equations are just the same. It's amazing. So here is the crossover surface, and here is this burst of radiation coming up here. It remains finite, and although you might say, well, it's got an infinite distance to go, that's squashed down, and the squashing down the Maxwell's equations are quite happy with. It just goes down to a certain value that you would have from that amount of stretch. And then on the other side, they'd have that much value. So the I guess that's your question. But the gravitational radiation you have to worry about because of the difference in the scale factors. And so as gravity, it gets scaled out, and then it appears as these error bonds on the other side. But you wouldn't see the error bonds directly in the previous eon. You just see them, you wouldn't see the error bond decays directly. You might see how they would affect the microwave background. It's a bit technical to go into, but yes, it's useful to think of infinity as sitting there, and as long as you're doing massless physics, that's fine. And you don't have to worry about things scaling away or whatever it is, because the scale is taken care of by this picture.
Okay.
So,
Up in the back.
so I'll ask. Oh, sorry.
Oh, sorry.
I'll ask a much more simple question, hopefully. So I've always wondered if there's anything fundamentally that's conflicting here, assuming that our universe is inside a black hole, and whether the boundaries of our universe are solid or there is some exchange, and what are the laws outside of the boundaries of our universe?
Well, I would say if we're inside a black hole, the picture is nothing like this. You see, the picture is you just run into the singularity. The singularity is the great mess, which I showed you when I turned the universe upside down. And so that's when the gravity is, the entropy, if you like, is in the gravitational field. And in a black hole, it just makes a mess. And I wouldn't recommend being inside a black hole because you won't escape into the next eon. You've no hope of doing that. So that's part of the information loss business, is that there's no way of continuing it because the Weyl curvature blows up, and it's fortunate that that's inside a black hole and you don't need to worry about it, because in the continuation is what happens on the outside of the black hole.
Okay. Up in the back.
So does all physics look the same from eon to eon? I mean, same fine structure constant, same four forces, that kind of thing?
There's a good question there. And it's certainly conceivable, as maybe John Wheeler would have liked, is that the constants of nature get churned around every time they go through from eon to eon. And this is a rather alarming possibility. All I can say is they don't do much in certain respects. You see, one of the major big numbers that people worry about is think of a proton, think of a hydrogen atom, and then there's the force between the proton and the electron, and electrically and gravitationally. And the electrical force is about 10 to the 40 times larger than the gravitational force. And that number, 10 to the 40, or its square root 10 to the 20, and powers of 10 to the 20 seem to keep coming in different things. And you see it in the cosmological constant, as well as other parts of physics. Now, is it possible that that number gets changed as you go from one eon to the next? Yes, it is, and I certainly worry about that. I don't want it to change because I think it would muck my equations up, but that's just my personal feeling about it. But you could see that it probably doesn't change much because there is a limit. You see, the circle things, which I hope people will start believing in because the evidence is quite strong they are there, these circles have theoretically, there's a maximum size they could be, which is round about that in the diameter of the circle. And you see them pretty well, about that in the sky. Now, not that big. If you saw them that big, that would contradict this simple picture, and it would tell you that black holes, supermassive black holes, formed much, much earlier in the previous eon than they do in ours because of constants of nature thing. All I can say is it's pretty consistent with what we see in our eon. Now, a lot more work would need to be done on that, but there's no blatant change in at least the gravitational constant from what it was in the previous eon to what it is now. You can't tell much about the other numbers, but at least that's a bit of evidence which reassures those who, like me, who don't want them to change that much.
Okay.
If at all.
Next question, over on the left.
So the latest thing seems to be that the expansion of the universe is actually accelerating rather than constant. So does that mean your conformal mapping would be time dependent or keep getting bigger, or how does that work with an accelerating expansion of the universe?
I should explain that acceleration in the expansion is what I'm using. So that is the basis, or one of the bases, if you like, of this model. And that is what I've tried to draw here. You've got this exponential expansion, which means the acceleration is increasing exponentially. And so, yes, indeed, that's what we see. I was a bit shocked when I first heard it, not because I didn't know what it was, because I said, oh dear, that's the cosmological constant. In those days, I didn't want the cosmological constant, but I got persuaded, I think, by Jerry Oestreicher, that you really have to believe in it from the observations. And so I said, okay, I'll take it into consideration. But that is the one which you need to get this nice space-like conformal infinity. So infinity behaves in just the way you need for this model, and that depends crucially on that exponential expansion which is observed. So I'm using that. That's what you're talking about, I take it.
Yeah. Okay, we have time for one more question.
Yes. Does your theory have anything to do with the asymmetry of matter and antimatter in our universe?
It's an interesting question because, of course, people always used to worry about that. I should explain to people that it seems, as far as particle physics is concerned, every particle has an antiparticle which has the opposite charge and, well, the same mass, but most of its parameters are the other way around. So if it's positive charge, the antiparticle will be negative charge and vice versa. And what we see is in the massive version, the massive charged particle, which predominates, namely the proton, is positively charged, and the little massless one that goes around it, the electron, is negatively charged. But you could imagine that there are other parts of the universe it was the other way around, and there's nothing in theory to stop that. And then people worry, where did that asymmetry come from? And then they say, well, maybe in particle physics there was some very early particle, an X particle or something or other, which had an asymmetry in its decay with respect to one way or the other, and that's where it came from. It's possible. I'm not making a claim one way or the other here, but what I would say is that I don't need it in this model. I don't need it in the sense that if it's asymmetric now, or if it was asymmetric in the previous eon, that asymmetry would propagate to us. So we can put the blame on the previous eon, if you like. And people in the previous eon would be putting the blame on the one before it, and so on. But I mean, it's a scheme which makes sense. It doesn't answer the question of why it's asymmetrical, and maybe there's a deeper reason. But all I'm saying is that you don't need this asymmetrical decaying particles in the early universe in order to make sense of it. And it may be that it was just like that, and that they just kept on. It was like that right in the very, well, there's no earliest eon perhaps, and it just propagated from one to the next. On the other hand, maybe there was some early particle which decayed asymmetrically, and that's quite possible. I don't have an answer except to say that there's another answer to your question.
Okay, and with that, I would like to thank Sir Penrose. And we have one more thing. And at this time, I'd like to welcome Joan Schmeltz to come to the podium. She's the Sophia Associate Director for Science and Public Outreach, and she's going to close our program.
Thank you, Carol. So we'd all like to thank Dr. Penrose for his visit, but one member of the Sophia team, Leslie Proudfoot, had a very special way of saying thank you. Leslie couldn't be here this afternoon, but she wanted you to know that she has a fascination with Penrose tiles. Leslie is not only a talented artist, but she is also a wonderful baker. And we on the Sophia team take advantage of both of those traits often, maybe not often enough. Leslie baked cookies in the shape of Penrose tiles, in the kites and the darts, and you may have seen the display out on the tables outside of the auditorium, where she put those tiles together to form a beautiful star pattern. And some of you may have seen the display, some of you may have eaten the display, but Leslie wanted you to have a bag of those cookies. So these. So these are Penrose tiles baked by Leslie in deep appreciation for your lovely visit. Thank you.